In the last section, we looked at how you can describe the position of a complex number in the Argand diagram by saying its modulus and its argument. Next, we're going to look how we can write the complex number in what's called the modulus argument form. So let's say we've got this complex number z and its real part is x and its imaginary part is y. So we've got x plus iy. So that means that we've got this coordinate xy on the complex plane in the Argand diagram. In this section, we're going to come up with a shorter way of writing modulus of z. We're not going to write modulus of z like this all the time. We're just going to use the letter r. So r is going to stand for the modulus of a complex number. So that length there is r. And instead of writing arg z, we're going to use theta to represent the argument of a complex number. So we know that theta is that angle there because we've moved around in the positive direction, so theta is positive. So we can come up with some expressions that help us find out what x and y are. So let's suppose that we only know r and theta. We only know the modulus and the argument. Well, we can draw in a right angle triangle like this, and we can come up with some equations for x and y. We know that cos theta is adjacent over hypotenuse. The adjacent length on this right angle triangle is x, so that's x over r. So that gives us a really useful formula for finding x. X is equal to r cos theta. So that means that if we know the modulus and the argument, then we can find out what x is. Similarly, we know that sine theta is equal to opposite over hypotenuse. The opposite side length in this right angle triangle is y. So we know that sine theta is y over r. So that gives us a really useful formula for finding out y, the imaginary part, r sine theta. What the modulus argument form does is it says, well, this is one way of writing this complex number, x plus iy. Another way of writing this complex number would be to replace x with r cos theta. And we could replace y with r sine theta. And then normally we take out the common factor of r outside of a bracket. So we'll have r bracket cos theta plus I sine theta. And this form here is called the modulus argument form of the complex number z. The reason why we say it's in that form is because the only information we need to write the complex number in this form is the modulus and the argument. And this formula works for all values of theta. As long as theta is measured in the way that we always have been for the argument, so measured positive direction is anti-clockwise from the real axis, then this will work no matter what theta is. Normally, theta will be the principal argument, so between minus pi and pi, but it wouldn't matter if you used an argument between 0 and 2 pi, for example. Let's try and write this complex number z in modulus argument form then. So we need two pieces of information to put it in this form, this modulus argument form. We need r, the modulus, and theta, the argument. So I'd always recommend drawing a sketch of the Argand diagram and plotting the point. So the real part is minus root 3. And the imaginary part, we've got 1i, so the imaginary part is 1. So let's draw in our line to the origin. So r is going to be the length of this line. So we can draw in a right angle triangle, and we can just use Pythagoras to work out that right angle triangle, the length of r. So we know that r is equal to the square root of root 3 squared plus 1 squared. You could also use the formula for r, which we looked at in the last video, which is r is equal to the square root of x squared plus y squared, where x is the real part and y is the imaginary part. So if you use that formula, you'd be doing the square root the real part is minus root 3 and the imaginary part is 1. Okay, so you get r is equal to 2 in this case. So we found our modulus. Next we need to find out the argument. So the argument is going to be this angle here, and it's going to be a positive argument because we're moving in the positive direction. Let's call that angle theta. So we need to find out, let's find what alpha is first using this right angle triangle, and then we can find out theta by doing pi minus alpha. So we know that tan alpha is equal to opposite of this right angle triangle, which is 1, divided by the adjacent length in this right angle triangle, which is root 3. So we'd get that alpha is arctan of 1 over root 3, which is pi over 6. So we know that theta must be pi minus pi over 6, which is 5 pi over 6. And then we just check it is positive, so we don't need to make it negative because we've moved in the positive direction. So that tells us that theta is 5 pi over 6, so we can write z in modulus argument form. So z is equal to 2 cos 5 pi over 6 plus I sine 5 pi over 6. Now the reason why that works is because we're basically saying that if we expand this, then we have 2 cos 5 pi over 6 plus I times 2 sine 5 pi over 6. And the way that trigonometry works is that this part here is going to be equal to minus root 3, and this part here is going to be equal to the imaginary part, which is 1. The reason why this works is to do with the unit circle, which we'll look at in another video.